Projectile motion example video 5. Once again, we are talking about an angled motion because we're giving an angle. So in this case, Evan is on his skateboard. He's jumping off a ramp that is at 40 degrees, and he's going at 9 meters per second. And he's leaping from one ramp to another, identically heighted ramp. And we need to figure out how high up he's going to go. So that will be going across like this. We've got the displacement on the y-axis, and of course we have acceleration due to gravity. And then we have displacement on the x-axis, there. That will be for the second part. We should go ahead and do this part immediately before we forget. We have 9 meters per second at 40 degrees. That is like our resultant, so I need to break it down into the x and y. My y, of course, being r times sine of theta, and then my x being r times the cosine of theta. And I can actually do the solving for those later on. Looking at my y-axis, let me go ahead and list out everything. Initial velocity, final velocity, acceleration, displacement, and time. Initial velocity, plugging in the 9 times the sine of 40, that is going to give me 5.785 meters per second. My final velocity, because I'm talking about at the peak, that final velocity is going to be 0 meters per second. Acceleration is, of course, going to be little g, negative 9.8 meters per second squared. Displacement is what I'm looking for. And then time, I don't care about just yet. I will later on, but not just now. So that means I'm going to use the VF squared equals VI squared plus 2AD. The final velocity is 0, so that goes away. Bring the VI squared to the other side, so that's going to be negative VI squared equals 2AD. Divide through by twice A. That all cancels, and I tap into my calculator, and I get D equals 1.7075 meters. With reasonable significant digits, that would be 1.7 meters. That was my displacement on the y-axis. That is the peak height. Now, while I'm speaking of the peak, I'm going to go ahead and use another equation. This time I'm going to be solving for the time, and I'm not going to care about displacement on the y. The reason I'm doing that is I'm going to be solving for the hang time, because the hang time up here is going to help me getting the hang time going across. That's the same time for the x. So, not caring about my displacement, it's an easy equation. VF equals VI plus AT. Okay, the final velocity once again is equal to 0, so negative VI equals AT, dividing both sides by A. And I go ahead and plug in, and I get time is equal to 0.59 seconds. T equals 0.59 seconds. Now, as we pointed out, that's only for the first part. For the second part, it's going to be the same amount. So I've really got to figure out my hang time is taking this and multiplying by 2, and that would equal 1.18 seconds. Now you say, where am I going to be using that? Well, that hang time on the y-axis is going to be the same hang time as on the x-axis. So listing out the stuff for the x, I've got velocity on the x, displacement on the x, and the time. Velocity on the x using the r times cosine theta. That is going to be, let's see, Tapping into calculator, 9 times cosine 40 is going to be 6.89 meters per second. Displacement on the x is what I am looking for. And then the time is the time that I gotten before, so that is 1.18 seconds. So easily done. I'm going to say displacement on the x, velocity on the x, times the time. So tapping into my calculator, I get the displacement on the x, that's how far away it needs to put the ramp, is 8.1 meters.